Hello, today we're going to be talking about complex numbers. And I actually really like what we're doing today. I think it's kind of funny. We finally get to answer the age-old question of what happens when you have a square root of a negative number under a radical. But obviously, before we kind of get started on that, I'm going to ask you guys to try the Ignite at the top of the page. All right, answer is up. It's kind of a little bit of an obnoxious answer, but you should have got this guy as your final answer. 3 root 10 plus 10 root 2 plus 4 root 5 plus 6 all over the square root of 11. So if we look at kind of the steps, your first step in order to simplify was recognizing that, remember, you are not allowed to have square roots on the denominators of fractions. So our first step was to go about rationalizing the denominator. And to do that, you multiply the denominator by basically the same exact quantity, whatever's down here, except for we change the sign. Because what that does is when you actually distribute those polynomials together, it's going to cause the two middle terms with the square roots to cancel, first of all. And over here, when I do root 5 times root 5, we get the square root of 25. And the square root of 25 ends up being 5. Now the top, really nothing about the top is super nice. We don't really have any really like terms, but you do have to remember that we do want to simplify any of the radicals. Now, if you look at some of the other ones, like if I look at root 10 or root 5, those are about as simplified as this goes. But root 50, on the other hand, is something that can simplify. So that's what I did over here. I simplified 2 root 50, and you should have got 10 root 2 for that. So all I did was plug that back in for 2 root 50, and nothing else really simplifies. On the denominator, all I did last was 9 minus 20, and you get your answer of negative 11. Okay? Now, the nice thing about today is that when we deal with complex numbers, we're going to talk about what they are in a moment. The nice thing is that a lot of the same properties that are true for radicals are also true for complex numbers. Now, the cool thing about complex numbers is you've actually worked with them before. You just didn't know it. Like, for example, when you dealt with radicals last year, you might have come across a problem or two where you were left with a negative number on the inside of the radical. And if you actually type this into your calculator, it tells you error. And the reason is, usually says like error, unreal answer, or something along those lines. And there's a very specific reason why that is. Your calculator only deals in real numbers, but there are such thing as numbers out there called unreal answers. And so complex numbers, just so you guys know, complex numbers, there's really kind of like 3 words we use to kind of all mean that same thing. So we can say complex numbers. One of the more popular ones is called imaginary. So we can call them imaginary numbers. And what they are they're basically non-real answers. And it happens in very specific cases. In this specific case, when you have a negative on the inside of a radical. So when that happens, and we start to go through and simplify. If you take off this one, by the way, when we go ahead and simplify, the answer is not error. It's not no solution. It's that now that we're kind of working in this new realm of numbers, there actually is an answer to this. Up until this point, pretty much Algebra 1 only deals in the real world, the real realm of numbers. We also deal with rational numbers, so like fractions, and things, and natural numbers are just like the non-decimal answers. But in complex world, we start to enter the realm of the non-reals or the imaginary numbers. So like I have the meme up here. The nice thing is that I don't know if this helps you remember this, but the imaginary numbers are they are the negatives on the undersides of radicals. So for example, if this square root of 16, this negative normally in the real world of numbers, we would say our answer would be no solution. But the that square root of negative 1 actually means something else. It means, we call it I. So usually the non-real answers, just so you guys are aware, I'll almost always use a cursive I, just because my eyes sometimes get confused. They look like ones sometimes. But whenever we have that negative on the inside, our answer is not no solution anymore, because we're in a different realm of numbers. That square root of negative, that negative under the square root, what happens is we pull it out in front of the radical and we simplify the number inside just like we would normally. So for example, this one, square root of 16. Square root of 16 is actually a nice number. It's 4. And the I would just stay as part of your answer. So if I see square root of 17, now this one is a little bit odd in that I can't actually take the square root of 17, but I have a square root of a negative number, which means square root of the negative, the I would come out in front. And we would simplify what's inside, but square root of 17 just doesn't simplify anymore. So we just leave it as I root 17. Now, you might be kind of thinking this through in your head. You're like, Ms. Hardy, that I, it's basically like a variable, right? The answer to that is absolutely not. It follows some of the same qualities that variables do, and you'll see where we go with that in a little, like down below in some of our notes examples. But I is actually a number. It's the square root of -1, which means if I wanted to square I, we would take square root of -1. Ooh, wow, sorry. I would take the square root of -1 and we would square it. And if you type that in your calculator, the squared and the square root cancel, and you get -1 as your answer. So there are cases where if we have an I squared, we are allowed to replace the I squared with a -1. But we always take just the plain old negative on the inside of a square root. That always comes out in front. So a lot, like for example, if I say simplify the square root of square root of -288, we still start with, now we start with the imaginary step. So we say, okay, well, it's a negative. Normally that would mean no answers, but now square root of -288, that negative is going to come out in front. And now we're just going to simplify 288 just like we would normally. So I actually want you guys to do that now. I want you to simplify 288, pause your video and give it a shot. Final answer, you should have got 12i root 2. If you simplify the square root of 88, or 288, excuse me, you might not have done my first two steps, but at the ends of all of your branches, you should have had a set of 2s, a set of 3s, another set of 2s, and there's 1 2 that doesn't really have a buddy. So that one just goes back on the inside. And we multiply any of the other sets together. So that's how you get your final answer. So really nothing changes. Even like number 2, even if we're dealing with a quotient, we still start with the square root step. We start by taking, wow, that I didn't work. If I take out the negative underneath the square root as an I, we're going to start again by simplifying what's on the inside. So pause your video for just a sec. I'm going to fill in this work. If you simplified square root of 120 correctly, you should have gotten 2 root 30. So if we place that back in our problem here, just like all other quotients, though, remember, we do want to check kind of that one last step. And our one last step is to double check to see if anything reduces outside of the radical. So I'm looking at 6, 2, and 10, and I know for a fact that they all reduce by a factor of 2. So final answer is to actually divide them all by 2. Now remember, the radical doesn't count. You can't divide something in a radical with something outside of a radical, but 10 divided by 2 is 5, and we are left with our final answer. So when it comes to radicals, or when it comes to expressions involving I, we solve them very similarly as if it was a variable. So page number 2, really this is just working with different types of operations with I. And just like when we deal with quadratics, if we say write the expression as a complex number, just like quadratics, imaginary numbers have really a typical form that we're going to use. It's called standard form. And what it looks like this. It's a plus or minus bi. And the reason why all this really means is that any numbers that don't involve an I, we always typically write first, and anything that involves an I is always written second. It's just kind of how complex numbers work. So for example, even if we're going to do sums or differences like the first 2 problems, these guys we still tackle kind of as if it was a variable. We have to keep in the back of our minds that it's not actually a variable, but just like any other expressions, we still kind of follow the same typical rules. If there's parentheses, we still would distribute anything out in front. So this guy, 1, if I distribute the 1 to my first set of parentheses, we're left with 8 plus 2i. If I distribute the 1 to my second set of parentheses, we're left with 3 minus 7i. And just like we would with variables, here we're going to go through and combine like terms. So for example, anything without a variable, I'm going to go ahead and add together. And anything with a variable, just like if it was a variable of x, we would still add the numbers together. So 2 minus 7, and that's going to give us -5. And the I would stay with it. Addition or subtraction doesn't change what your variable is. Multiplication and division, on the other hand, that could possibly change it, but we'll get to that in just a moment. Even on like number 4, we still would say, okay, to get rid of the parentheses, I would distribute. We would be left with 15 minus 3i plus 2 minus 4i. And again, combine like terms. 15 plus 2 would leave us with 17. And -3 minus 4 would leave us with -7i. Now, this is true standard form. If you switch those, what standard form means is that we do not write our answer like this. We don't write the I term first and the number second. It's always going to be flipped around. So what I want you guys to do, pause your video, and I want you guys to try number 5. You should have gotten 25 plus I for your final answer. So so for this one, again, if you distribute all the numbers in front, the biggest one to be careful with is the last set of parentheses. You had to make sure to distribute a -1 in front. Now, even when we transition to not necessarily multiplication or division, it does help to pay attention what's happening to the numbers in front. So like in these problems, if these were really just distribute the number in front of the parenthesis and then combine like terms. But really, that was mainly focused on adding and subtracting. Here, we're going to transition into some multiplying and dividing. And again, just like variables, we still would go through and we would multiply to each thing on the inside. And we multiply like things together. So -3 times 2, just like that, those are the numbers that I would multiply together. And the I would stay with it. I would multiply -3 times 6 together, and we would get -18. And just like variables, I times I becomes I squared. Just like x times x would become x squared. But here's where, in complex number world, we are not done. Because if you'll remember from the first page, I is not a variable. I is technically a number if you think about it at the end of the day. And specifically, now we don't usually replace I with the square root of -1, but we will always replace I squared. Because I squared is actually a really nice number. I squared actually equals -1. I did write that on the first page, but I figured I'd write it again. So in complex number world, that is always, if there's ever an I squared in the problem, that is always going to be one of our next steps. You should never have an I squared left over in your final answer because you can always simplify. I can do -18 times -1, which is +18. And then last step is to write it in standard form. Woo, it's going to be 18 minus 6i. Okay. So even when we go about multiplying a binomial together, again, we still kind of follow the same steps as if it was a variable. I would start by doing my first 2 terms. 2 times 3 is 6. I would do my outside terms. That's going to leave me with 8i. Then I'm going to move on, multiply my inside terms. That's going to leave me with 24i. And last but not least, I'm going to multiply the last 2 terms together, and that's going to leave me with a -32. I times I is I squared. And we're not done for multiple reasons. First and foremost is because we have like terms. So let's go ahead and add those together. If I take 8i minus 24i, that leaves me with -16i's. And we're still not done because, again, we have an I squared in here, which means I can actually go through and replace that I squared with -1. And now there's one more thing I can do. I can multiply those guys together, and that's going to leave me with +32. And now I can add my numbers together. 6 plus 32 is going to leave me with 38. Bring down the -16i. And now you're done. So what I want you to do, pause your video, and I want you to try example 8 on your own. Final answer, you should have got 45 minus 35i. After you distributed, you should have been left with this step. And remember, there's two things we can simplify. We can combine the two middle terms together to get negative 35i. And because you have an I squared in here, you can replace that with negative 1. So, but if you look at all the answers to these, they all follow true standard form. A number plus something times that, plus or minus something times I. A number plus or minus something times I. All of them, you're going to notice, you do not have an I squared in any of your problems. Now, when we work with some of the denominator or the fraction ones, these are ones where kind of like when we have radicals on the denominator, if ever we say simplify and there's complex numbers involved, we are not allowed to have i's on the denominator either. But what's nice is it's not a crazy new process. It's the same process we use. It's the same process that we use. Same process that we use for when we rationalize the denominator with square roots. We take what's on the denominator and we change the sign. Because this kind of we want to do the same thing that we would do with square roots. We want to get rid of all square roots on the denominator. So by multiplying by what's on the denominator, look at what happens. If I do my first two, 1 times 1 ends up being 1. 1 times 4i is going to end up being 4i. Negative 4i times 1 is going to leave me with negative 4i. And already I love what's happening because already 4i minus 4i, these are going to cancel. And look what happens on the end. 4i times, negative 4i times 4i is going to leave me with a negative 16i squared. But in complex world, I squared, we can replace with negative 1. So the cool thing is that basically the same steps kind of apply. Now, we do have to multiply what's on the numerator though. So let's multiply that through now. 7 times 1 is 7. 7 times 4i is going to leave me with 28i. And then last but not least, 5 times I is going to leave me with 5i. And 5i times 4i is going to leave us with 20i squared. So again, we combine like terms. Now keep in mind, some students like to do this all in one step. This 20i squared really is 20 times negative 1, which really means you're subtracting 20. So if you want to do that kind of in one step, you can. Really, numbers wise, I want to do 7 minus 20. And at the end of the day, that's going to give me a negative 13. Now, my middle terms, we have 28i, and I'm going to add the 5i together. That's going to leave me with 33i. And now I just have to really simplify the denominator because this negative 16 minus 1, negative 16 times 1 ends up being a positive 16. So when we go about simplifying on the denominator, really what we have is we just have a 17 on the denominator. And I'm going to bring down my numerator. Now, typically, remember, we're also kind of in a fraction world. We're in all bunch of worlds right now. We would check to see if these numbers simplified. They don't. So that just means for us that this is my final answer. So what I want you to do, again, pause your video, and I want you to try example 10 on your own. All right, final answer, you should have got 1 minus I all divided by 2. Now let's see how we got that. First step was the rationalizing the denominator step. So you should have multiplied your numerator and denominator by 4 minus 2i, because on the denominator you have a 4 plus 2i, and we want to do the opposite of that. It's called the conjugate. So when we do that and you multiplied, you should have got the following over here. Okay. And then all I did on my first step was I started simplifying. So on the numerator, I just did negative 6i minus 4i and got negative 10i. On the denominator, I did negative 8i plus 8i, which cancels, so they're gone. And then all I did was I simplified the I squared pieces, because I squared is I can replace with negative 1. So when you do that, this becomes a minus 2 and a plus 4. And all I did was then combine like terms. So I did 12 minus 2, and we got our 10. And then obviously on the bottom, 16 plus 4 ends up being 20. Now be careful, because a lot of students want to stop here. A lot of students want to stop here. Nope. Struggle. A lot of students want to stop here, but we have to remember to reduce. So if they all reduce by a factor of 10, which leaves us with our 1 minus I all divided by 2. Okay? So obviously if you look at the next page, I have a whole bunch of different you try now problems that involve all of basically the problems that we just did. So if there are any particular ones you want to try, I'm going to write in the answers. So if you would like to try any of them before knowing the answer, pause your video now. All right, answers to the first 4 problems are here. And then I'll scroll down a little bit, and then there are the answers to the last kind of 2 problems. Okay, so as always, now's the perfect time where if anything didn't make sense, you know what to do. Reach out, email Miss Hardy, and ask to go over some problems.